thanks to the organizers for the invitation. It's a real pleasure to be able to speak in this seminar. So I want to sort of continue from where Shin left off and talk about some more recent developments in the min-max theory for constant mean curvature hypersurfaces. Okay. And so the talk is going to have two main sort of parts. So in part one, I want to discuss this min-max theory in some non-compact spaces. And so there are two main examples I want to consider. The first is the prescribed mean curvature problem in Euclidean space. And the second is the constant mean curvature problem in asymptotically flat spaces. And then in the second half, I want to introduce this idea of the half volume spectrum of a manifold. And so this is recent joint work with Shin. Okay. So I want to start with the min-max problem in non-compact manifolds. So remember that we have this AC functional, which takes in an open set, and it tells you the area of the boundary minus C times the volume. And so Shin and Jonathan Ju proved that there is a min-max theory for this AC function. So in particular, if you take some closed manifold of dimension between 3 and 7, then there is a min-max theory that you can use to find smooth critical points of this AC function. Or in other words, constant mean curvature hypersurfaces with mean curvature C. And in particular, using this, you can check for every C, there is a CMC hypersurface in M. Okay, and so the question I want to ask is, well, this theorem is on a closed manifold, so what can you say if M is not compact? And again, there's sort of two settings I'm going to consider. The first is the prescribed mean curvature problem in Euclidean space. And the second is the constant mean curvature problem for an asymptotically flat manifold. Okay, so I'll start with the PMC problem in Euclidean space. And so again, here, the motivation is the following problem of Weyl from his list of problems in differential geometry. So he asks, for which functions H on R3 can you find an embedded two-sphere whose mean curvature is prescribed by H? Okay, and so for this talk, I want to consider a related question in higher dimensions, namely, for which functions H on Rn+1 can you find a closed embedded hypersurface whose mean curvature is prescribed by H? Okay, so we've allowed the dimension to go from 3 to greater or equal 3. And we've sort of dropped this assumption on the topology of the surface we're finding. Okay, so this is sort of a natural higher dimensional analog from the point of view of geometric measure theory. You can increase the dimension, but the price you pay is that you lose control over the topology of the surfaces you're finding. So let me explain some previous work. So in general, Yao's problem is still open. But Calderoli and Messina have studied Yao's problem in dimension 3, so they have the original Yao problem using the mapping method, meaning they look at maps from S2 into R3, which are critical for the Dirichlet energy plus a certain H-weighted volume term. And so using this, they give the following sufficient condition. So assume you have a function H on R3, and it satisfies the following assumptions. So first of all, it's asymptotic to a positive constant at infinity. Secondly, the radial derivative decays suitably fast as x goes to infinity. And third, a certain mountain pass energy level is not attained at infinity. And I'll say more about what that means in a moment. And then the conclusion is that in these circumstances, then there exists a branched immersed two-sphere in R3 whose mean curvature is prescribed by H. So the first main theorem you can think of as sort of a higher dimensional analog of this, which is proved using geometric measure. All right, so the theorem is, let's suppose the dimension is between 3 and 7, and we take a prescription function h on Rn plus 1, and it satisfies essentially these same three hypotheses. So it's asymptotic to a positive constant at infinity. The radial derivative decays at a suitable rate. And a certain min-max value is less than this constant alpha of n plus 1c. And again, I'll say what this means in a moment. And then the conclusion is that then there exists a closed, almost embedded surface, or hypersurface, okay, with mean curvature prescribed by h. So in comparison with the previous theorem, you have sort of the usual differences between something proved using the mapping method and something proved using geometric measure theory. So Calderoni and Messina, they get control over the topology, they get a two-sphere, but they only get something which is branched immersed. Whereas here, we lose control over the topology, but we get something which is almost embedded. Okay, so let me try to explain what this condition 3 means. So remember, we have this AH functional. So AH of omega is the area of the boundary minus this H-weighted volume term. Okay. And so I want to consider all the continuous families of open sets, starting from the empty set and ending at some set where this functional is negative. Okay, so you can think of like a family of expanding spheres. It starts from the empty set. Eventually, the set has really large volume. So this H-weighted volume term is going to be very negative. And so this functional becomes negative. Okay. And then we define the min-max value. So we look at all families like this. For each family, we find the set where AH is the largest, and then we try to minimize that over all the families. Okay, so this defines the omega. All right, and so then what is this constant? So the alpha of n plus 1c. So here we look at the literal family of expanding balls in Rn plus 1. And we find the maximum of the AC functional over that family. Okay. And so you can check that this is equal to the value of AC on the ball whose mean curvature equals C. Okay. So this constant, it is the min-max value when the prescription function is identically this constant C. Okay. So the min-max value omega, it's always less than or equal to this constant alpha, since H is asymptotic to C at infinity. And so we can always open up a family of balls near infinity, and the maximum along that family is very close to alpha of n plus 1c. Okay, so this assumption that we have strict inequality is supposed to ensure that these balls near infinity are not achieving the min-max value. And so there's something interesting happening in the compact portion of the manifold. So I want to sort of sketch the proof of this. And so the main idea is we'd like to apply min-max for the AH functional over these previously described families. But the trouble is, okay, we're on a non-compact manifold. This min-max theory of Shin and Jonathan, it only applies on a compact manifold. And moreover, there are sort of no barriers at infinity for this AH function. So you sort of can't constrain the problem to some compact piece of the manifold. Okay. And so the idea to get around this is you introduce some cutoff functions. So for each radius r, I want to let zeta r be a cutoff function, which is 1 inside the ball of radius r, and it's 0 outside the ball of radius r plus 1. All right. And then I want to form these cutoff prescription functions HR, which is zeta R times H. So it equals the original prescription function H inside BR, and it's 0 outside BR plus 1. So the point is that now this AHR functional agrees with the area functional near infinity, and so there are barriers near infinity. So large coordinate spheres serve as a barrier to minimal surfaces. And so you can sort of confine the min-max problem for this AHR functional inside BR plus 1. And so then you can apply Shin and Jonathan's min-max theory to find a surface sigma R contained in BR plus 1, whose mean curvature is prescribed by HR. And so then to finish the proof, you want to check that this surface sigma R is actually contained inside BR, which is the region where HR agrees with the original prescription function H. So this is what you need to do to solve the problem. And so suppose for contradiction that this is not true. Suppose that the sigma R always intersects this transition region between BR and BR plus 1. So you can prove that the surfaces sigma R have uniform area and index bounds, and so you have some compactness, and you can pass to a limit as R goes to infinity. Okay, so this is illustrated in this picture. So we have the surface sigma R. It's intersecting this region between SR and SR plus 1. Inside SR, our cutoff prescription function agrees with the original. And outside SR plus 1, the cutoff prescription function is identically 0. So we pass to a limit as R goes to infinity. And we're going to see some surface sigma infinity. These pieces of the spheres are going to become vertical planes. And because H is asymptotic to C at infinity, HR is going to limit to a function H infinity, which is identically C to the left of this slab. It's identically 0 to the right of the slab, and it decreases monotonically from C to 0 as you go across. And the thing I want to argue is that this sigma infinity actually must be contained to the left of this slab where H infinity equals C. So suppose that's not true. Suppose H infinity hits this transition region. And then the observation is, well, then you can apply Alexandrov reflection. So start bringing in this blue plane from the right. As you cross sigma infinity, you start to reflect. And you keep going until the first time that the reflected surface touches the original surface. In the picture, that's this red slice. Okay. And then look at this point Q where these touch. So on the one hand, the sort of red reflected part is contained inside the black original part. So the maximum principle tells you the mean curvature of the red part must be larger than the mean curvature of the black part. Okay, but on the other hand, at this point Q, the mean curvature of the black part is H infinity of Q. And the mean curvature of the red part is H infinity at this reflected point. Okay. And so since H infinity is monotone decreasing, the mean curvature at this reflected point, okay, H infinity at this reflected point is strictly less than H infinity at Q. Okay. And so that gives you a contradiction because it tells you actually the mean curvature of this inner piece is less than the mean curvature of the outer piece. Okay. So this Alexandrov reflection argument tells you that actually this surface sigma infinity must be contained in the region where H infinity equals to C. And so in particular, this tells you that sigma infinity must just be a sphere with constant mean curvature C. Okay. And so then you obtain that on the one hand, as R goes to infinity, AHR of sigma r converges to the min-max value. And on the other hand, as r goes to infinity, AHR of sigma r converges to AC of sigma infinity, which is AC of a ball with mean curvature C, which is this constant alpha of n+1c. And so you get that the min-max value is equal to this constant, contrary to assumption. So the main idea is you solve this sort of family of cutoff problems, and then this assumption on the min-max value together with the Alexandrov reflection argument tells you that these solutions to the approximate problem can't drift off to infinity. So this is the problem for PMCs in Euclidean space. The next non-compact problem I want to consider is in asymptotically flat manifolds. Okay. So we say a manifold is asymptotically flat if you can find a compact set K contained in M and a diffeomorphism from M minus K to R3 minus a ball. And in the coordinates induced by the diffeomorphism, the metric approaches Euclidean sufficiently rapidly as x goes to infinity. So an example is the Schwarzschild metric with mass m. So this is a metric on R3 minus a ball of radius m over 2. Okay, with this metric conformal to Euclidean. And if you think about this being embedded in Euclidean space, it sort of looks like a piece of a catenoid. The boundary of this ball, radius m over 2, is this sort of minimal slice here. And as you go off to infinity, you become sort of asymptotically flat. Okay, and then another example is doubled Schwarzschild. So this is the same metric, but on R3 minus 0. And so this looks like two copies of the previous example glued along the minimal boundary. Okay. So Shin asked the following question. So suppose we have an asymptotically flat manifold. Can you always find a closed embedded CMC hypersurface in M for every value of C? Okay. So let me make a few remarks. So if we look for sort of closed embedded hypersurfaces, then this isn't true in Schwarzschild with the minimal boundary. And so this follows from work of Brendle. He classified all the CMCs in Schwarzschild with the minimal boundary, and the only ones are the fibers. Okay, and you can check there are no fibers with very large mean curvature. Okay, so I'm going to restrict to asking this question for asymptotically flat manifolds without boundary. Okay, if you wanted to include boundary, you could also pose the question for finding free boundary CMCs in the asymptotically flat manifolds with boundary. But for this talk, I want to consider the case of no boundary. So let me try to give some motivation. So there's a theorem of Huskin and Yao from '96, which says if we have a manifold M3G, which is asymptotically flat, and in particular, it's strongly asymptotic to Schwarzschild. So the metric very nearly resembles Schwarzschild near infinity. Then you can find a foliation by CMC spheres near infinity. Okay. Okay. And so that they showed that these spheres can be used to define a center of mass for M. And this has since been generalized by many people, Eichmer, Korber, Wang, Metzger, Nertz, and so on, to allow for sort of weaker assumptions about how the metric approaches Euclidean at infinity. Okay. So this kind of tells you what's happening at very large scales in your asymptotically flat manifold. What about very small scales? So there's a theorem of Weyl, which says if P is a non-degenerate critical point of the scalar curvature, then you can find a small neighborhood of P which is foliated by CMC spheres. Okay, and so if you put these two observations together, suppose you have some generic asymptotically flat manifold with no boundary, then okay, somewhere in the interior, you expect there should be a critical point of the scalar curvature, P. And near P, you have this foliation by CMC spheres. Right, so near this point P, you have CMC spheres with really large mean curvature. And on the other hand, near infinity, you have this Huisken-Yau foliation. That gives you CMC spheres with very small mean curvature. And so it's natural to ask, well, what's happening in the middle? And we also find CMCs for the intermediate values of H. Okay, so I can give a partial answer to this question. So assume M3G is some asymptotically flat manifold with no boundary, and choose some positive constant C. Okay, and again, I need to make some assumption about the min-max value. So assume the AC min-max width is less than this constant, 4 pi over 3 times 2 over C squared. Okay, then the conclusion is there exists a closed, almost embedded CMC hypersurface in M. Okay. So again, what is this min-max width? So it's defined very similarly to the previous example. So again, we want to consider continuous families of open sets, starting at the empty set and ending at some set where AC is negative. Again, you can think of like a family of expanding balls. And then we define the min-max value as follows. So we look at all such families. For each family, we find the set whose AC value is the largest, and then we try to minimize that over all the families. Okay. And so what is this constant? So the constant 4 pi over 3 times 2 over C squared. This is the maximum of the AC functional in R3 evaluated on a family of expanding balls. Right, so the area of the boundary is 4 pi r squared. The volume is 4 pi over 3 times r cubed. Okay, and the maximum here is this constant. So in the previous notation, this was called alpha of 3c. And this is the min-max width for AC on Euclidean R3. So the assumption again is that the min-max width on the manifold is strictly less than the min-max width on Euclidean R3. Okay. All right, and so the proof of this is very similar to the previous result. You introduce this family of cutoff min-max problems, which admit barriers at infinity. And then you use this Alexandrov reflection argument together with the assumption on the min-max value, okay, to show that these solutions can't drift to infinity. So maybe I should at least say something about scalar curvature. So this assumption that the min-max value is strictly less than 4 pi over 3 times 2 over C squared is sort of not very nice. This is not really a natural geometric condition to impose on your manifold. And so the question is there some sort of more geometric condition that we can impose on our manifold, which implies the condition about the min-max value? Okay. Right, and so on an asymptotically flat manifold, the natural guess for such a condition is non-negative scalar curvature. Okay, so my conjecture is if you have an asymptotically flat manifold with non-negative scalar curvature, and you fix any constant C, then this assumption about the min-max value is true, unless M is actually isometric to Euclidean space. Okay, and so I can give some evidence for this. So So first of all, let me suppose I have some family of metrics GT on R3, starting at the Euclidean metric. And suppose that at time 0, the derivative of the scalar curvature is positive on a sufficiently large ball. Then you can check that the min-max value for GT is strictly less than this constant for all small enough positive t. So a deformation tending to increase the scalar curvature is tending to decrease this min-max value. Okay. And so some more evidence. So Brendle and Eichmer studied the isoparametric problem in the Schwarzschild manifold. And in particular, okay, in the Schwarzschild manifold of mass M, so this is not Euclidean, but it has scalar curvature identically 0. Okay, and they show that you can find a smooth family of open sets beginning at the empty set, ending at a set of arbitrarily large volume, and such that the isoparametric ratio is well controlled along the entire family. Okay, so on the right-hand side, 36 pi to the 1/3, this is the isoparametric ratio of a Euclidean ball. And so this says the isoparametric ratio is strictly less than the Euclidean one everywhere along this family. And so you can use this to check that on the Schwarzschild manifold of mass M, the min-max value is strictly less than the Euclidean value for every choice of C. So the conjecture is also true on Schwarzschild. Okay, and then I'll just say, okay, as a corollary of this, on doubled Schwarzschild, this assumption is true. And so the theorem says doubled Schwarzschild has an almost embedded CCMC surface for every choice of C. All right. Okay, so this is sort of the conclusion of part 1 of the talk. So this is the min-max problems in non-compact spaces. Okay. And so now I want to go on to part 2, which is to introduce this idea of the half-volume spectrum of a manifold. And so this is joint work with Shin. And so I want to sort of change the perspective. Okay, so far, sort of everywhere in my talk and also in Shin's talk, we've always sort of fixed this Lagrange multiplier C. Okay, and then we looked for critical points of the AC functional, right, on this entire space C of M. And this produces CMCs whose mean curvature is equal to C. But there is another way that we could try to find CMCs. Namely, we could impose some volume constraint. Okay, so there's a comment in the chat. It's a paper. Maybe I can look at this after the talk. So suppose we fix some number V between 0 and the volume of M, and we try to find critical points of the area functional subject to the volume constraint, that the volume of omega is V. So if we succeed in finding critical points, this produces CMCs enclosing volume V. Okay, but there's no control over the precise value of the mean curvature. So as opposed to the previous approach where you fix the Lagrange multiplier, there you get precise control over the mean curvature, but no control over the enclosed volume. Here you get precise control over the enclosed volume, but you lose control over the exact value of the mean curvature. And so the min-max problem with volume constraint is sort of much less well studied than the min-max problem with the fixed Lagrange multiplier. But nevertheless, we sort of expect there should be a rich existence theory for this problem, at least in the case where V is half the volume. And so this is what I want to discuss for the rest of the talk. Okay. So first, I need to tell you what is the usual volume spectrum. So let's suppose we have some closed manifold, Mn plus 1G. And so Gromov proposed the volume spectrum as a kind of nonlinear analog to the spectrum of the Laplacian. So let me first give some informal definitions. So we say a family of hypersurfaces, sigma t, parameterized by t in some space x, is called a p-sweepout if no matter how you choose p points in M, you can always find a surface in your family passing through all p of those points. So, for example, the level sets of a Morse function on M form a one sweepout. And likewise, if you take the family of sort of all p tuples of level sets of a Morse function, then this is a p sweepout. So in this picture here, I have S2. My Morse function is the height function. Okay. And so the level sets of the height function are a one sweepout. I mean, no matter what point I pick in the manifold, there is some level set passing through that point. Okay. And to get a two sweepout, a surface in my family would look like some pair of level sets. So if you give me any 2 points in the manifold, I can always find a pair of level sets that passes through both of those points. Okay, so sort of more formally, let me let Z of M, Z2 be the space of all codimension 1 mod 2 flat cycles in M that are homologous to 0. So for the purpose of the talk, you can just think of this as smooth hypersurfaces in M, which are homologous to 0. And the topology on this space is that two hypersurfaces are close together if they bound a region of small volume. Okay. Right. And then I'll let C of M be the space of Cacciopoli sets in M. You can just think of this as open sets with smooth boundary. And here the topology is that two sets are close together if the volume of the symmetric difference is small. So Marquez and Neves proved that the boundary map from C of M to the space of cycles is a double cover, and that the space C of M is contractible. So essentially C of M is like S infinity, and this cycle space is like RP infinity. Okay. And in particular, the cohomology ring of Z of M, Z2 is the cohomology ring of RP infinity, Z2 adjoin lambda, where this generator lambda is in degree 1. So then more formally, we can define a p-sweepout as follows. So it's a continuous map phi from some parameter space X into this space of cycles, such that the pullback of lambda to the p is not zero. And so then for each p, we can define a min-max value called the p width of M. So omega p, you look at all p sweepouts. For each p sweepout, you find the surface in the family of maximal area, and then you try to minimize that over all the p sweepouts. And so this defines this number omega p. And the sequence omega p is called the volume spectrum. And this is supposed to be some kind of nonlinear analog to the spectrum of the Laplacian. So Gromov conjectured that this volume spectrum should satisfy a Weyl law. Okay. All right. So Gromov and then later Guth showed that for a given manifold M, these p widths grow sublinearly like p to the 1 over n plus 1. Okay, so there are constants C1 and C2, so that you grow at least like C1 times P to the 1 over n plus 1. You grow at most like C2 times P to the 1 over n plus 1. And then later, Lyubomirsky, Marquez, and Neves showed that Kromov's conjecture was true. So you can find a universal constant depending only on dimension, so that these P widths grow like this constant times the volume to the n over n plus 1 times P to the 1 over n plus 1 as P goes to infinity. Okay, so I want to talk about the half volume spectrum. And so again, let me be informal at first. So I again want to consider a family of hypersurfaces in M, but I want to make the additional requirement that each of these must enclose half the volume of them. Okay. And then given this additional requirement, the definition is the same as before. So we say this family is a half volume P sweepout if for each choice of P points in M, there is some surface in the family passing through all P of these points. So here, this picture is illustrating a half volume 1 sweepout of S2. So we start with this equator and we rotate it around to build the family. Each of these surfaces in the family encloses half the volume of M. And given any point in S2, there is some surface in this family passing through. Okay, so more formally, let me let CH of M be the space of Cacciopoli sets whose volume is equal to half the volume of M. These are the open sets whose volume is half the volume of M. And I want to let H of M Z2 be the cycles, which bound a set whose volume is half the volume. This is the space of half volume cycles. Okay. And so the observation is that this space of half volume sets inherits this Z2 action, sending a set to its complement. Right? If omega has half the volume of M, then the complement of omega also has half the volume of M. And so because of this, you expect that the space H also has a rich topology. So the first fact is that the space of all Cacciopoli sets, this deformation retracts to the space of half volume Cacciopoli sets. And this deformation retraction is equivariant with respect to this Z2 action, sending a set to its complement. And so in particular, this descends to the quotients and it gives a deformation retraction of the full cycle space onto the space of half volume cycles. So this space of half volume cycles also has the topology of RP infinity, and its cohomology ring looks like Z2 adjoint. So then given this, we can make the same definitions as before. So a half volume P sweepout is a continuous map from some parameter space X into the space of half volume cycles, so that the pullback of lambda to the P is not zero. And so then we can define the half volume P width of M, omega P tilde. So it's a min-max value. We look at all half volume P sweepouts. For each one, we find the surface of maximal area, and then we minimize that over all the half volume P sweepouts. And so this sequence omega P tilde is the half volume spectrum. So let me try to give some motivation for maybe why you would want to consider this. So this half volume spectrum, it's another kind of nonlinear spectrum you can associate to a Riemannian manifold. And so one thing I'll say is that this usual volume spectrum, it sort of has some similar properties to eigenvalues of the Laplacian with a Neumann boundary condition. So what I mean by this is, if you look for eigenvalues with a Neumann boundary condition, the way to do that is you do min-max for the Rayleigh quotient on sort of all of W12. And here the natural operation is restriction. So if M decomposes into two pieces, U and V, if I have a W12 function on M, I can restrict that to a W12 function on U and to a W12 function on V. Okay. And so for the volume spectrum, the test space is this full cycle space. And again, the sort of natural operation is restriction. If I have some cycle in M relative to the boundary of M, I can restrict that to a cycle in U relative to the boundary of U, and a cycle in V relative to the boundary of V. Now, on the other hand, the half volume spectrum, it behaves sort of more similarly to eigenvalues of Laplacian with a Dirichlet boundary condition. So when we look for eigenvalues with a Dirichlet boundary condition, we look at the Rayleigh quotient on the space W120, which is a smaller space. Restriction sort of no longer makes sense. Right? If M is decomposed into U and V, and I have a function vanishing on the boundary of M, when I restrict to U, there's no reason it should vanish on the boundary of U. But instead, the natural operation is gluing. Right? If I have a function vanishing on the boundary of U and a function vanishing on the boundary of V, I can glue to get a function vanishing on the boundary of M. And if I look at this half volume spectrum, again, my test space is this sort of smaller space of half volume cycles. Okay, restriction no longer makes sense. If I have something enclosing half the volume of M and I restrict to U, there's no reason it should enclose half the volume of M, or of U, sorry. But instead, the natural operation is sort of gluing. Right? If I have something enclosing half the volume of U and something enclosing half the volume of V, I can glue those together to get something enclosing half the volume. Okay. So these are sort of some just abstract motivations. For us, really the reason we thought of this is thinking about this sort of twin bubble problem, trying to find two CMCs on a given manifold. And we found that these half volume CMCs can act as an obstruction to certain methods for trying to find the second CMC. All right. So we thought, well, maybe you can perturb away these half volume CMCs, and then you can find a second CCMC. But then when you think about it, you realize, well, actually there are sort of topological reasons you should expect that there are always many half volume CCMCs or half volume CMCs. And so this approach sort of doesn't seem like it should work. Okay, so what are sort of the main results? So we can prove that this half volume spectrum also satisfies the Weyl law. So the omega p tilde grows like Cn. So this is the same constant from the Weyl law for the usual volume spectrum, times the volume to the n over n plus 1 times p to the 1 over n plus 1. So this is sort of, it's not super hard to check this. So the first observation is being a half volume p sweep out is a more stringent condition than being a p sweep out. And so that immediately tells you omega p tilde is greater or equal omega p. And on the other hand, it's not so hard to convince yourself that every p plus 1 sweep out contains a half volume p sweep out. And so that gives you this other inequality. Omega p tilde is less or equal omega p plus 1. And so then your omega p tilde is sandwiched between omega p and omega p plus 1. And then you can appeal to the Weyl law for the usual volume spectrum, okay, to get the growth of the omega p tilde. Okay, so then the final thing I want to talk about are finding some surfaces associated to this half volume spectrum. Okay, so in the minimal case, there's a theorem of Marquez and Neves, okay, which uses Shin's resolution with the multiplicity one conjecture. So it says if we have a generic metric on a manifold, closed manifold of dimension between 3 and 7, then for every p, there's a smooth minimal surface, okay, whose area achieves omega p. And so we'd likewise like to know if there are some surfaces achieving this half volume spectrum. So perhaps the optimistic conjecture would be for a generic metric G on a closed manifold dimension between 3 and 7. Well, the best you could hope for is that for each P, you can find some smooth CMC enclosing half the volume of M and whose area achieves this omega P. So, well, we can't prove this. And in fact, in sort of the Allen-Cahn setting, there's still no, at the moment, there's no real theorems for doing min-max with a volume constraint. But there is another min-max theory for finding minimal hypersurfaces in CMCs. This is the Allen-Cahn min-max theory. And so the idea is you take some double well potential W, okay, and for this W, you define for a parameter epsilon and a function U, this energy. It's the integral of epsilon over 2 times gradient U squared plus W of U over epsilon. And suppose for each epsilon, you have a critical point of E epsilon. So then the idea is as epsilon goes to 0, the W term should force U to become plus or minus 1. And the gradient term should penalize the transition from minus 1 to 1. Okay. And so in fact, under sort of suitable assumptions, as epsilon goes to 0, these U epsilons will converge to a limit U infinity, which is plus or minus 1 almost everywhere. And this limit interface between the plus 1 part and the minus 1 part is a minimal surface or CMC. Okay, so many people have worked on this problem. Hutchinson, Tanagawa, Roger, Tanagawa, Wickramaseckera, Bellettini, Wickramaseckera, and so on. Okay. And so what I'll say is, so in the minimal case, Gaspar and Guaraco defined an analog to this volume spectrum. So they call it CP. They proved a Weyl law for the CP, and they constructed minimal surfaces associated to the spectrum. Later, Day proved that actually the volume spectrum and this phase transition spectrum are literally identical. They're the same for every P and N. So we can also define an analog to the half volume spectrum in the Allen-Cahn setting, CP tilde. And we expect, although we haven't proved, that this should equal the omega P tilde. Right, so I think I'm almost out of time, so let me wrap up. Okay, so we can use the the Allen-Cahn min-max theory to find some surfaces associated to CP tilde. And so this uses an existence theorem of Bellettini and Wickramaseckera for finding sort of CMCs and PMCs in the Allen-Cahn setting. So, so this theorem, it's sort of an analog of the CMC and PMC existence theorem of Shin and Jonathan, but in the Allen-Cahn setting. So sort of applying this result, we get the following. So assume we have a closed manifold of dimension between 3 and 7. Then for each p, you can find an open set whose volume is half the volume of M and whose boundary has constant mean curvature, together with some possibly empty collection of minimal surfaces, sigma 1 through sigma k. And you can find some multiplicities so that Cp tilde is achieved by M0 times the area of boundary omega plus M1 times area sigma 1, k plus dot 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 out through mk area of sigma k. Okay. And finally, these multiplicities associated to the minimal surfaces are even. And this multiplicity associated to the CMC is always 1, okay, unless the CMC is also 1. Okay, so I think I'll stop here. So thank you for listening.